Right, hello everyone and welcome back. So in this video I'm gonna solve a very hard, very long problem from partial fraction decomposition. Okay, so still we are in the case where we have an irreducible factor in our decomposition, so we want to integrate this rational function. Okay, so the rational function that is given is 1 over x plus 6 times x square plus x plus 4. X square plus x plus 4 is an irreducible factor, so the decomposition can be given like this. Okay, so I have already given you the decomposition. I want to save the time, but I highly suggest you to figure out the decomposition by yourself. Okay, pause the video, try to get this same answer, same numbers and functions. Alright, so integrating this function is same as integrating its decomposition. Okay, so I have done some work here to save time. So we want to integrate the right hand side of the decomposition. Then integrating the first part is very easy. 1 over 34 times x plus 6. It's a linear factor in the denominator, so the integral is going to be, well, we can take 1 over 34 outside the integral, so integral of 1 over x plus 6 is natural log x plus 6. So this is what we get if you integrate 1 over 34 x plus 6. Okay, all right, so the focus here is how to integrate x minus 5 over 34 times x square plus x plus 4. All right, so we saw similar kind of problems in the previous video, right, in previous couple of videos. All right, so here this is a little bit complicated. The problem here, what you have to integrate here is a little bit complicated. Now why is that? So let's compare. All right, so this is the two cases. So in this problem we want to integrate x minus 5 over x square plus x plus 4 with respect to x. Now in the previous video we have something like to integrate x square plus 4. The difference is we didn't have the middle x term that we have here in previous problems. This is what we had in previous problems. So in previous problems what we did is we know our substitute is going to be x plus 4, right? We use a combination of integration by substitution and the tangent inverse rule, and derivative of the x plus 4 is 2x. So what we did here is we have this minus 5 as an obstacle, so we split the function, right? We split the rational function as x over x square plus 4 minus 5 over x square plus 4. We divided each term in the numerator by the denominator. That's what we did, right? Okay, so we can do that. Well, we did that because, well, 5 was an obstacle and we didn't have a constant term in our derivative, right? We just had that x term. Now look at the problem that we have right now. Well, we know our substitute. We are still going to use a combination of integration by substitution and tangent inverse rule, but our substitute is going to be x square plus x plus 4. Okay, we talked about the reason for this choice in 2 videos ago, right? Now the derivative of u here is going to be 2x plus 1. Now here's the difference. Now in our derivative we have this constant term, okay? And I mean this minus 5 is still an obstacle, but our derivative is much complicated than what we had here, okay, than what we had in previous problems. Okay, all right, so how are we going to handle this? The main difference here is that having this x term will yield a constant in the derivative, okay, when you choose your u to be that denominator x square plus x plus 4. All right, so how do we handle this situation? All right, so why is it so important that we talk about the derivative of the substitute? Derivative of u. What is the role that this derivative plays when we use integration by substitution? Well, in any integration by substitution, I mean in most of the problems, the role that this derivative plays is something like this. Think about something like this. Think if your problem is like 2x plus 1 over x square plus x plus 4, and if you use this substitution, okay, what's going to happen is this is 2x plus 1, this is now u, dx is du over 2x plus 1. See what's going on? That derivative will cancel to help certain terms in the integral. So the idea here is if we had if we had 2x plus 1 on the numerator, my bad, in the numerator, then life would be much easier. Like, I mean, if we had this rational function to integrate, then life would have been much easier, okay? All right, but we are not that lucky. So what can we do here? Okay, so I mean, x minus 5 and 2x plus 1 are two totally different things. What can we do here? The trick here is, what we are going to do is we are going to create 2x plus 1 artificially in the numerator. Okay, how can we do that? Let's do this step by step. Okay, so stay focused. So first thing, if you want to create 2x plus 1 in the numerator, coefficient of x should be what? 2, right? So multiply everything in the numerator by 2. So if you multiply numerator by 2, you have to divide denominator by 2, right? So you multiply and divide by 2. So what's going to happen is we are going to utilize this 2. So it's 2x minus 10. So I multiply the numerator totally by 2. Does it make sense? Okay. So this 2 stays here outside the integral. It's in the denominator. So 34 times 2 is what? 68. Okay, is it negative? Yes, so there should be a negative. All right, perfect. Okay, so try to understand what I did. So again, the purpose is to create 2x plus 1. So I need plus 1, not negative 10. What I'm going to do here? So I want plus 1 in the numerator, right? So let's add a 1 artificially, but at the same time, let's subtract a 1. So adding and subtracting 1 will make no difference, right? If you add a 1 and subtract a 1 immediately, 1 minus 1, 0, it's still 2x minus 10. Can you see that? 2x minus 10 and this expression that I have here is same thing. Okay, adding 1 and subtracting 1 doesn't make any difference. Okay, but it's a trick. It's a very useful trick in mathematics that we use. So now I'm gonna filter out that 2x plus 1 term, because that's the nice term. Minus 1 minus 10 is minus 11. So I'm gonna rewrite this numerator like this. Okay, so actually this is still 2x minus 10, but it's written in a different way, right? We're kind of like doing a trick, like cheating sort of, right? Okay, so now we have 2x plus 1 in the numerator. So what is the obstacle now here? Now the obstacle is minus 11, just a constant term, right? Now what can we do about that obstacle? Well, we can do the same thing that we did in our previous problems. We split the rational function. Okay, so we have minus 68 and we are going to split. I mean, we are going to divide each term in the numerator by the denominator. By each term, I mean, first I will divide 2x plus 1, that whole thing, by x square plus x plus 4 minus, now I'm going to isolate that 11 over x square plus x plus 4. All right, so this is what I'm going to do. So I will have a big bracket to make sure that negative 1 over 68 is outside. Okay, so let's rewrite this problem. Okay, so what do you have? 1 over 34 natural log x plus 6 minus 1 over 68, a big bracket, integrate 2x plus 1 over x square plus x plus 4 with respect to x, and minus integrate 11 over x square plus x plus 4. Okay, all right, so this is what we have. All right, okay, so now the middle part, if you want to integrate the middle function, so let's integrate 2x plus 1 over x square plus 4. So the substitute is u is x square plus x plus 4, du over dx is 2x plus 1. So if you use integration by substitution, let's make space, 1 over 34 natural log x plus 6. So this is 1 over 68, 2x plus 1 over u, dx is du over 2x plus 1, right? From here 2x plus 1 cancel out, so it's just we are integrating 1 over u, right, with respect to u. All right, minus, let's work on this integral later, okay, because trust me, it's harder than what we have seen what we have seen already. Okay, so if you integrate 1 over u, you get natural log u, right? Natural log x plus 6 minus 1 over 68 bracket, this is natural log absolute value of u, so it's actually x square plus x plus 4, right? All right, because u is x square plus x plus 4. Now we don't know whether x square plus x plus 4 is negative or positive for sure, so let's keep the absolute values. All right, so does this make sense? Let's take a quick recap. So what did we do here? So we are done with the second part. What did we do here? Well, we had a complicated denominator because we had a full quadratic function, because we had this x term. Okay, so we use our denominator to be the substitute in the integration by substitution. So we predicted the derivative, which is 2x plus 1. So we artificially created 2x plus 1 in the numerator. Okay, so by doing so, we created this extra negative 11 terms. So we split the numerator, we split the rational function. So for the first half, we did integration by substitution. For the next half, well, what are we going to do for the next half? So let's take that integral separately. Integrating 11 over x square plus x plus 4. Now, as I said before, so for this is a constant of a quadratic function, so we are gonna use the tangent inverse rule. But we have a complication here. So the tangent inverse rule says, if we have sum of squares, sum of x square plus a square, then you can use tangent inverse rule. But again here, look at this problem. We have this x term as an obstacle, right? X square is there, okay, 4 you can think as 2 square, but what are we going to do with that x? Because in the rule we don't have this x to the power 1 term. What can we do here? Another complication. Well, the idea is somehow we have to write this x square plus x plus 4, that whole function, as a sum of 2 squares. Somehow we are going to drop that x term. How can we drop that single x term? Well, we learn something like that when we are learning trigonometric substitution problems, harder trigonometric substitution problems. We are not going to do trigonometric substitution, but we use some sort of a trick when we are learning trigonometric substitution problems. The trick is completing the square. Okay, so if you have forgotten completing the square method, click on the link that appears in this video and watch that video, review completing the square method, and come here. Okay, so we don't have time to review completing the square method in this video, but here's the idea. So the goal is to write x square plus x plus 4 as a sum of 2 squares. Drop that x term. So to do that, what I'm going to do is, the method of completing the square is that take the coefficient of the term that you want to drop, the x term. The coefficient is 1, so divide it by half. Okay, so if you divide 1 by half, you get, when you divide 1 by 2, not by half, okay, divide 1 by 2, so you're going to get half. So what you're going to get is, so then you can write, once you get that number, write it as x plus half square. So this half come from 1 dividing by 2. Always divide the coefficient by 2. So take x plus half square. What you're going to get? X square plus x plus 1 over 4. That's x plus half square. Now, this function is almost same as x square plus x plus 4. So we have to make an adjustment. Alright, so what we are going to do is, well, we gonna say x square plus x plus 4 is actually x plus half square. Okay, and we want x plus half square, which is, okay, well, x square plus x plus 1 over 4 plus how much we need to make 4, how much more we need to add to create 4 here. So we already have 1 over 4. How much we need more to add 4 to get 4 here? So let's see how much we need. It should be a fraction. So it should be a 15 over 4, right? So if we add 15 over 4, we get 16 over 4 here, and then we get 4, right? Okay, so we know x square plus x plus 4 is x plus half square plus 15 over 4. So all of a sudden, from x square plus x plus 4, we get only 2 terms. Okay, so we can write this function as, now we want to integrate 11 over x square plus x plus 4 with respect to x. So all of a sudden we can write this as x plus half square plus square root of 15 divide by 2 square. Now all of a sudden it's a sum of 2 squares. So 15 over 4, if you want to write it as a square, you can take the square root of 15 and divide it by 2. Square root of 4 is 2. So if you square this, you get 15 over 4, right? That's what I did. Alright, so now I have a sum of 2 squares. So we get this by completing this square method. Alright, okay, so now using the tangent rule. Well, in the tangent rule we have x square, but instead of x square we have x plus half square. But x plus half here in this problem play the role of x. So x is actually a placeholder. So instead of x we have x plus half. So this is, so what is a? So a square, so square root of 15 over 2. So that's our a. Alright, I know it's a little bit ugly. So it's 1 over a, 1 over square root of 15 over 2. Tangent inverse, x is now x plus half, divide by a is square root of 15 over 2. Wow. So that's the answer for this integral. Okay, solution of this integral. So let's write the full answer, full solution. So the full solution for the decomposition is like, alright, 1 over 34 natural log x plus 6, 1 over 68 natural log x square plus x plus 4, negative, here I can write this as 2 over square root 15 taking the reciprocal, tangent inverse x plus half times 2 over square root 15, close the bracket, plus arbitrary constant of integration. Okay, so that's a big complicated problem, right? I mean, this is a very complicated problem, so you should approach this very slowly. Okay, stop this video, pause this video, okay, try to learn it step by step. I don't think it's very easy to follow right away from the video. Okay, so what you should do is try to learn the reason why I did each of these steps. Okay, the reason behind these steps, understand the steps, try to convince yourself, try to understand what's going on step by step. Okay, it was a lot to cover. All right, so that's it for this video. Thank you very much.